Let's take a look at Newton's first two laws and also what we mean by the particle model when we talk about forces acting on objects. Okay, so in order to model a situation and describe a force acting on an object, what we're going to do is we're going to treat, and this is the particle model, we're going to treat all objects as though their mass is concentrated at a point. So when you draw diagrams and you want to visualize forces acting on an object, just imagine all of the mass of that object is at its geometric center somewhere. Okay, so place the dot somewhere, geometric center ideally, but just imagine that's where all the forces are acting through. Okay. Geometric center does not mean the same as center of mass. Okay, it depends on, because geometric has to do with shape and center of mass has to do with distribution of mass, including density and so on. So we're just concerned, the particle model, throughout these videos here, we're just going to place the center, the entire mass of the object, we're going to imagine is at the center, the geometric center of the object, and we're going to apply all our forces through that point when we draw our diagrams and calculate net forces. Okay, so the momentum is the mass times the velocity. So momentum is a vector, it has a magnitude, and it also has a direction. Mass times velocity, so a body of mass 5 kilograms is moving at v equals this vector here, meters per second, and so P is m times v is 5 times that, kilograms and meters per second. Okay, Newton's first law says a body continues in its state of rest or uniform motion in a straight line unless acted upon by an unbalanced force. So an object remains still or moving with a constant velocity unless some force acts on it. Gravity, a push, a turn, a pull, what have you. All right, Newton's second law, the time rate of change of momentum, where momentum is P equals mv, is proportional to the resultant force and acts in the direction of that force for as long as that force acts. So d dt, the derivative with respect to time of the mass times the velocity, which is the momentum, is m times dv dt, is the mass times the acceleration vector, is equal to force. Force is a vector, has a magnitude, and it has a direction. So force vector is equal to mass times the acceleration vector. All right, so let's have a look at an example. We've got here, that's it. Three forces, F1, I plus 3k, F2, 3i plus 2j plus k, F3 is I plus 2j minus 2k, act upon an object of mass 10 kilograms. Find the acceleration. Okay, well, total force on the object, F total, will be F1 plus F2 plus F3. And when we add all those together, we add the I components together, so 1 plus 3 is 4, plus 1 is 5 in the I direction. In the J direction, 2 plus 2 is 4 in the J direction. In the K direction, 3 plus 1 is 4, minus 2 is 2. Okay, so there's our force vector. We know that the total force, or is the net force acting on the object, is equal to the mass of the object times its acceleration vector. Well, we found the force total is 5i plus 4j plus 2k. The mass is 10. The acceleration vector at this point is unknown, but we now have 10 times a is equal to the net force on the object, and so the acceleration, we just divide through by 10. The acceleration vector is 1 on 10 times that net resultant force, meters per second. Working that through, we get 0.5 I, 0.4 J plus 0.2 K. All right, that's that.